In this example, I would like to explain shear force and bending moment in the beam. When you see this figure, on the left side in the A, the pin is attached like this one. On the right side here, the roller is attached. And on the left side, maybe there is some freedom in movement. It's not moved left and right, ups and downs. It's not moved, but rotation is free. On the right side, movement in horizontal direction is okay, but it doesn't move at all ups and downs. That's the restriction. Here at this point, L over 4, at this point, concentrated force is acting like this one. And in the middle of the beam, we have moment, twisting moment is acting like this one. Moment is acting like this one. Okay. Here, our final goal, our goal is to find shear force and bending moment. Where? Inside the beam. This location and this location and this location. We would like to know that. In order to do that, we must have a quick review about bending convention, the direction convention for bending moment. When you see this figure again, shear force, the positive direction is like this one. On the right side, downward direction is positive, and on the left side, upward direction is positive. And when you see the moment, in the case of bending moment, on the right side, counterclockwise direction is positive. Okay, we can apply this kind of sign convention to this problem. Okay, let's go back to this problem. At first, let's think about the RA and RB value first. Okay, in order to find this one, we can have force equilibrium, sigma F equals 0. Let's say this direction is positive. Then we do not have any forces in x direction. And we can think of this direction as positive Fy, let's say Fy. Then on the left side, Ra minus P and Rb equals 0. It is in the state of equilibrium. Okay, next one. We can think of moment. Let's say this direction is positive. Moment, let's say around this point, A point, equals 0. It is in the state of equilibrium. Okay, then P multiplied by L over 4. This direction is minus value. Then next, this one is also minus value, minus MO. And this one, let's say RB, and the length, total length is, how long is it? L. It's 0. Then we can calculate RB equals like this one. MO is divided by L, and plus L is deleted, and 4 PL. This one is RB. And when you apply this value to this equation, then we can also find RA value, like this one, this RA value. Of course, RA and RB is some forces which is written in Newton. Okay, we've calculated RB and RA value. we know RA and RB value. This value we calculate. Next, we would like to calculate what shear force V and moment, bending moment M. In order to find that, actually we can divide it into three parts. This part and this part and this part. Okay, when we introduce this distance is x. Firstly, when x is in this range 0 to L over 4, in this range, then we can draw a free body diagram like this one. This one is A, let's say, on the left side, A. And here we have RA value, RA, right. On the right side, when you cut somewhere here, let's say this distance is x. And we can introduce here, downward direction is positive, let's say V. And this one, moment, M is like this one. Then we can calculate here in this range V equals what? RA. V equals RA. Okay. Then M is what? M, bending moment. When you think about around this position, V is deleted, M, and RA x value is this amount of 1. Okay. We can calculate shear force and bending moment in the case of when x is in this range. Okay, next step we can consider this case. When x is in the L over 4 and L over 2, this range. Then we can think of this one, RA, P, and this distance is x, let's say. V is downward and moment is like this one. Then we can calculate V equals V, shear force V is same as RA minus P, RA minus P. Okay, next. When you think about moment, when you consider this amount 1, moment, let's say this one is positive, moment M equals, at this point, x point, let's say, x point 0, then V is deleted, M plus P. This distance is what? Let's say this distance is x minus this distance, L over 4. Then RA is minus RA, and distance is x. Then we can find here, we can calculate V value and this moment we can calculate. Okay, just apply this free body diagram. Finally, when you consider at this range here, from there to there, in this range, let's say in the case of x locates L over 2 to L, in this range. Okay, when you draw free body diagram is like this one. Let's say this one. This point is A. This one is RA. Let's say here P. and somewhere there is MO. Of course, this distance is up there is L over 4. Of course, here also L over 4. Up to there, let's say its length is x. Okay, we can introduce here shear force is acting like this one, V, and moment is acting like this one, M. Moment is acting like this one, M. Then we can calculate V value. Sigma F in this direction is positive, then RA plus RA and minus P, and here downward direction minus V equals what? 0. Okay. Then we can calculate V value here. Next, when you think about moment, let's say this direction is positive, then moment M equals 0, which is in the state of equilibrium. Let's say this position, let's say point X is considered. At this point, X point is considered. Then moment M is positive and V is deleted, and minus M, 0. And let's consider this one. Plus P is multiplied by this distance minus X minus L over 4. Okay. Next one, finally, this one. Plus, not plus, minus value, because we considered this one is positive. RA is multiplied by this distance, X. Okay. Then we can calculate what? Moment, this moment. We can calculate by applying in the equilibrium relationship. Then we can find shear force and bending moment for each case. In this example, we would like to calculate shear force and bending moment. At first, we've considered RA and RV value. When you apply total system, when you think about total system, and when you apply force and moment in this case, then you can calculate RA and RB value. Next, we've considered the 3 steps. First one is in this range, the first range. Second one, when this range. And finally this range. When you consider this, when you separate each cases, the first one you can calculate shear force and bending moment like this one. And in the second case, when you apply equilibrium relationship, then V and moment can be calculated. And finally, if it is located in this range, then force equilibrium, moment equilibrium, then you can find shear force and bending moment for each case. Okay, that's it for finding shear force and bending moment. Okay, in this example, we would like to calculate shear force and bending moment inside the beam. Actually, we have here cantilever beam. This cantilever beam is attached to point B, which is fixed to the wall. And In this case, when you draw free body diagram is like this one. You can introduce a beam, and external force is given this amount. Okay, of course on the left side is A and this point is B. When you isolate this kind of one, then we can draw like this one. Let's say RB and this amount 1. Let's say moment MB. The free body diagram is okay. This one is Q0 and the length is, let's say, L. This length is L. On the left side. Length is L. Okay, now we would like to calculate RB and MB. We would like to calculate. At first let's think about RB value. Sigma F equals 0. F. Upper direction is positive. Then we can say RB. Next, this distributed load. Actually, this, when you consider this distributed load, is equivalent to some forces is like this one. It is equivalent to this concentrated load. We can say the area of a triangle Q is we can calculate Q equals this distance, triangle area 1/2 L and this length or quantity Q0. That's the Q. Maybe Q is written in Newton meter, not Newton meter, just Newton. Normally Q0 is expressed in Newton per meter or millimeter. Normally distributed load is expressed in Newton per meter. Okay, if you know large Q is like this one, Q is like this one. Q is acting somewhere here. Its location is this distance is 2L/3. That's the point of location of position of centroid. Then we go back to this one, sigma F. This one is Q, large Q, and minus direction, large Q, instead of large Q, 2Q0L. That's the RB. 2Q0L. That's the RB. Okay, 2Q0L. You do not have any other force. Next step, we will consider moment. Let's say this direction is positive moment. Let's consider this point, B point. It is in the state of equilibrium, and moment. This one, let's say MB minus MB, and this direction is positive, plus Q, and distance is total length is L, and 2L/3, then 1L/3. L/3. That's the positive one. Then it is in the state of equilibrium. That's why MB we can calculate. MB equals Q is like this one, and 1 over 2 Q0L, this one is Q, and L3 is multiplied. Then finally 1 over 6 Q0 L squared, Q0 L squared. That's the moment which is acting at this point. Okay, that's the reactional force and reactional moment at this point. Okay, next step, we would like to calculate the shear force and bending moment. Which location? At this location, X position. When you draw free body diagram, it's like this one, okay. Then downward direction is positive, and bending moment, this direction, counterclockwise direction, is positive. That's the free body diagram. And problem is this Q is located like this one. We would like to know this one, because equivalent concentrated force is acting like this one. This one is what? Let's say this one is QX, Q over X. Then this one is what? 1 over 2 triangle area, X, Q, X, QX. QX is what? QX over X. We have when you think about this triangle and the small triangle like this one, then Q0 over L. That's why QX can be calculated LX Q0. Okay, now let's think about F equals 0. Let's say this direction is positive. Then minus V, okay, plus downward, plus, this one is also minus, because we defined this one, minus 1 over 2 X, QX is X over L Q0, X over L Q0, X over L Q0, X over L. Okay, then we can say V equals minus 1 over 2 Q0 X squared over L. Okay, over L, 2L Q0 X squared. That's correct. That's the shear force. Shear force is given like this one. Shear force is like this one. Next step, we would like to calculate bending moment. Okay, let's apply bending moment M, not O, around this point. Let's say X equals 0. Let's think about this direction is positive. Then moment M, V is deleted, and when you consider this amount 1, it's positive 1 and 1 over 2 X QX XL over Q0, this one. And this one is force, actually. This one is force. And distance. distance is this distance, and this distance is what? X over 3, x over 3, x over 3, x over 3. This distance is x over 3, and m is given like this one, and 1 over 2 x and qx, x over L q0, x over L q0. And finally, we can calculate m is what? The direction is not positive. This one is positive. Minus 1 over 6. Okay. L q0 and x 1 2 3 exponential 3. Okay, we can calculate shear force like this one. Okay. Okay, now we've found shear force is like this one, and bending moment is like this one. Okay, when you integrate this one, shear force, then you can have a bending moment like this one. When you take a derivative of bending moment, you can have this kind of shear force. Or when you take another derivative, dv dx, then q0 lx minus. This kind of curve is available. And this one is what? This one is shear force, but not shear force. Just this one is force. Okay. When you just take a derivative, just take derivative of shear force, then you can have. Of course, this one is just a linear one. This linear relationship between x and f. Okay, x and f. Okay, there is some relationship between force and shear force and bending moment. Okay. Anyway, our goal is, our final interest is to find maximum value of bending moment. Okay, when you take this derivative dm dx, which is equal to 0, then this point x equals L point, the bending moment is maximum value you can have. Okay, anyway, when you see this one, just at first you calculate reactional force RB and MP, and next draw this kind of free body diagram, then calculate shear force and bending moment like this one. That's it for this example.